anisotropic material are those material in which the material properties are not same in all three reactions. Now, if we consider a anisotropic material, and we can correlate the stress and the strain quantity like this, where we can write the stress in a vector form. So if we see the stress normally can be written as a tensor form, where this is your sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, 23, sigma 31, sigma 32, and sigma 33. So here you can see the stress tensor can be written in a vector form, and similarly strain tensor also can be written in a vector form. Now if we write the stress strain relationship, then we can write the relationship like this, where sigma 11 equal to C1111 times epsilon 11 plus C1122 times epsilon 22, like that we can write. And here we can write the same stress strain relationship in tensor notation in this form. Okay, so sigma ij that is equal to Cij KL times epsilon KL. So C is here stiffness matrix, and S is here the compress matrix. Now here you just see for a fully anisotropic material. Fully anisotropic material means that your ideally anisotropic material. In such cases, we used to have our 81 elastic constant, 81 independent elastic constant. Now here you can see this is the size of 9 cross 1. Here this is 9 cross 1. So here we should do 9 cross 9. So here we'll have total 81 elastic constant for a ideally elastic material. Now, if you consider a ideal elastic material, if you consider a ideally anisotropic material or fully anisotropic material, in such cases, you will observe that your normal stress is causing sharing stress in other plane. So normal stress in one plane is causing sharing stress in other plane. Or other way, sharing stress in one plane is causing normal stress to the another plane. Other way, you can say that under axial loading, we can have shear deformations. Under axial loading, we can have our shear mode deformations. Under axial loading, we can have shear deformations. And this type of material behavior very unusual, and you may not be able to find such material. One more thing is you observe. Observe that stress tensor and our strain tensor is not symmetric. Okay, normally we used to have a stress tensor and strain tensor as a symmetric tensor. Normally we used to have stress tensor and strain tensor as a symmetric, but here for fully anisotropic material, we do not have symmetric stress tensor or the strain tensor. Now, if you consider that stress tensor is symmetric, that means sigma ij is equal to sigma ji, and if you consider epsilon ij is equal to epsilon ji, then we can reduce the material parameter. Okay, we can reduce the material parameter from 81 to 36. From 81 to 36, where if we consider sigma ij is equal to sigma ji, then here this side will be 6 cross 1, because 13 and 31 and 13 will be the same, 12 and 21 will be the same, and 23 and 32 will be the same. So here we can reduce from 9 to 6 component. Here also it will be 6 to 1. So here it will be 36. So for a material, for an anisotropic material where stress tensor and strain tensor is symmetric, in such cases we used to have 36 independent elastic constant, and we can write in this form. Okay. One more thing here, one more thing here, you observe that our stiffness matrix is still not symmetric. One more thing here, you just observe that stiffness matrix is still not symmetric. Only our stress tensor and strain tensor is symmetric. So this is our 36 elastic constant where we have only stress tensor and strain tensor is symmetric. Now here we just observe that we are correlating stress and the strain using C1111 term. This notation we can write in a shorter form. So we can write in a contracted notation where sigma 1 represents sigma 11, sigma 2 represents sigma 22, sigma 3 represent sigma 33, and sigma 4 represent sigma 23, sigma 5 represent sigma 13, and sigma 6 represent sigma 12. In the same way, we also can write the stiffness matrix in this form. Okay, so it's 2, 3 basically is 4. So sigma 2, 3 is sigma 4, sigma 1, 3 is sigma 5, sigma 1, 2 is sigma 6, sigma 1, 2 is sigma 6. Similarly, we can write 10 component also. Okay, now this is our contracted notation to correlate stress and the strain, to correlate our stress and strain. Now, here you observe that we have achieved 36 elastic constant for a material in which stress and strain tensor are symmetric, but our material parameter or stiffness matrix is not symmetric. Now here, if we consider the strain energy component, strain energy we can write as a half stress time strain. So here if we write this is stress and this is your strain, so here this area is basically the strain energy, and we can write as your half stress time strain. Again, we can write the strain energy like this, half Cij times epsilon j and epsilon I. Now, if we take the derivative, if we perform double derivative of the strain energy, we'll observe that we are getting Cij when you take the first derivative, with respect to epsilon I, and second derivative with respect to epsilon j, we'll observe that is your Cij. Now, if we take the first derivative with respect to epsilon j and then second derivative with respect to epsilon I, you can obtain Cji. Okay. Now, here you can see this component should be the same. Cij and Cji should be the same. Now, if we consider the strain energy principle and derivative with respect to strain component, we observe that stress matrix is to be symmetric. Now, here you just see if you have a anisotropic material where our stress tensor is symmetric, strain tensor also symmetric, and stiffness matrix also symmetric, then our number of elastic constant needs to be 21. So 21 means here we have 6, and then 5, 11, and then 4, 15, then 3, 18, 20, and 21. So for a anisotropic material with stress matrix material, for an anisotropic material where stress tensor is symmetric, strain tensor also symmetric, and stiffness matrix also symmetric, in such cases we used to have total 21 elastic constants. So this type of anisotropic material is categorized as a generalized anisotropic material. Okay. Still, this 20 number of elastic constant is too high, and it will be very difficult for us to analyze with 21 elastic constant. Moreover, you can observe that in this material there is no plane of symmetricity exist. In this material, there is no plane of symmetricity exist. Okay. Now, if we observe that there are many material which shows some plane of symmetricity. If the material shows one plane of symmetricity, we used to say that material as a monoclinic material. If the material possesses two plane of symmetricity, then we used to say orthotropic material. If the orthotropic material is to show 2 or 3 plane of symmetricity. Okay. Now we are going to see if a material possesses 1 plane of symmetricity, then how many elastic constant we can have. And if a material possesses 2 plane of symmetricity, then how many elastic constant we can have. Okay. You will observe that if a material is to possess a 1 plane of symmetricity, then our elastic constant reduced to 13. And if the material possesses 2 plane of symmetricity, then our elastic constant reduces to 9. Moreover, if we see that the third plane also showing symmetricity, then also you'll observe that material constant, the number of independent elastic constant, is not going to reduce further. So for an orthotropic material with a 2 plane of symmetricity or 3 plane of symmetricity, we used to have 9 elastic constant. Okay, we are going to see how we can reduce that, or what are the conditions we need to satisfy to have our monoclinic material or to have our orthogonic material, to have our orthotropic material. Now here, if we consider a material with 1 plane of symmetricity, that means we have a material, and in the material we have point P dash, and here with this side we have point P. You can observe that this material, the material here is showing the symmetricity with respect to XY plane. Okay, so here this side is Z and this side your Z dash. Now the material here it is our symmetricity with respect to our XY plane. Here we have P point and here we have P dash point. Now we can observe that stress component at P dash point is like this, and stress component at P point is like this, and we can correlate the stress component at P dash and P using this transformation matrix. And okay, now here you just see, for this case we should have sigma dash is equal to sigma x dash for a 1 plane of symmetricity. For 1 plane of symmetricity, our sigma x dash should be equal to sigma x. Similarly, sigma y dash should be equal to sigma y, and sigma z dash should be equal to sigma z. Now here, and tau xy and tau xy dash should be your tau xy. Tau xy dash should be your tau xy. Now here, if we consider this condition, here we just see the sigma x and sigma x dash. If we compare the equation 1 and equation 2, here you will observe that we have this parameter and this parameter here. Now, if you want to have sigma x dash equal to sigma x, in such cases, the C14 and C15 would be 0. Similarly, for our y dash, similarly for our sigma dash y, similarly for our sigma y dash and sigma y, C24 and C25 is 0. And sigma z, our sigma z dash and sigma z, we should have C34 and C35 equal to 0. Now again, if we consider that tau xy dash and tau xy is also symmetric, because we have assumed that this plane, here we have assumed this plane is symmetric. So if we consider the shearing stress here in this plane, then the shearing stress, if you observe from this side or if you observe from this side, should be the same. So tau xy dash should be equal to tau xy, and to achieve that, our C46 and C56 should be 0. Okay, now here we observe that for a monoclinic material where we have 1 plane of symmetricity, in such cases, our elastic constant reduces. Okay, and now number of elastic constant that will reduce, we have 2, 4, 6, and 8. So 21 minus 8, that is your 13. So for your monoclinic material, we used to have 13 independent elastic constant. Now, if we consider 2 plane of symmetricity, One is your XY plane, another is your XZ plane. If you consider two plane of symmetricity, you can further reduce the number of elastic constant. Okay, and here you just see that shearing strain in the YZ plane, shearing strain in the YZ plane could cause the shearing stress in the YZ plane only. Shearing stress in this plane could cause shearing strain in the YZ plane only. In that case, we can write that sigma YZ that is equal to 344 epsilon YZ plus 345 epsilon ZX. Okay, since shearing stress should only cause the shearing stress in that particular plane, so C45 must be 0. This also can be achieved using this condition that sigma XZ is equal to sigma XZ dash or sigma YZ is equal to sigma YZ dash. Okay. Now one more thing you should observe that the normal stress should not causes shearing stress in the other plane. The normal stress should not causes shearing stress in the other plane. So normal stress in the X direction should not causes shearing stress in the ZX and YZ plane. Okay, now to achieve that, that means if we are applying normal stress, then we should causes normal stress. That should affect only normal strain. Okay, and shearing stress should affect the shearing strain. To achieve this, this component must be 0. So C16, C26, C36 should be 0. Now here, if you consider the two plane of symmetricity, in such cases, we can further reduce the elastic constant, okay, to 9. For a orthotropic material, where we have two plane of symmetricity, we used to have 9 elastic constant, 9 independent elastic constant, okay, and we can write the stress strain relationship like this. Here we have total 6, 7, 8, 9. This is the stress strain relationship for a orthotropic material. Here you observe the shearing stress only causes shearing strain, and normal stress does not causes shearing stress in other plane. Okay. Now in orthotropic material we have assumed two plane of symmetricity. Okay, now if we consider one more plane, third plane also as a symmetric, you will observe that we are not able to reduce the elastic constant. Number of elastic constant with two plane of symmetricity and three plane of symmetricity is constant, that is your 9. Now, if we want to see what are the elastic constants is to come in a physical sense, then we have to write the stress strain relationship. Here we have written in terms of strain and stress here, and we have written that elastic constant like this: 1 by epsilon 1 by Ex minus mu xy uy mu zx z like that. Okay, so if you see, our 9 independent elastic constants can be calculated from this 9 component, 9 engineering constant. Okay, this 9 independent elastic constant can be obtained from this engineering constant. 9 independent elastic constant can be calculated from engineering constant, and this can be written in this form, and strain and the stress can be written in this form. So for orthotropic material, we used to have total 9 independent elastic constant, and that 9 independent elastic constant can be obtained from our 9 engineering constant, that is your Young modulus along x, y, and the z, shear modulus along x, y, and the z plane, and Poisson ratio also the z plane. Poisson ratio nu zy is equal to minus epsilon y by epsilon z, nu zs is equal to minus epsilon x by epsilon z, and nu xy is equal to minus epsilon y by epsilon x. Okay, so here you just see This is our compliance matrix, but this is our compliance matrix S, and this is our stiffness matrix C. Okay, and this compliance matrix the compliance matrix S. Okay, and here the component of this matrix can be obtained from our engineering constant epsilon x, epsilon y, epsilon z, Z modulus, and from our Poisson ratio. So here you have just see, here you just observe, here you just observe that for a orthotropic material, we used to have 9 component, okay, 9 elastic component, and that elastic component, this component of the displacement cal can be calculated from our engineering constant 9 engineering constant. Now, if you consider a transversely isotropic material is a material where we used to have isotropic nature in one particular plane. So here we are considering xy plane isotropic in nature. That means if we consider any point here, if we consider any point here, that our material property here Ex and Ey should be the same. Okay. So here this type of material we can say transversely isotropic material. That means this type of material is to have a one axis of the symmetry. So here Z axis is the axis of symmetry. To consider this type of material, in that case, our stiffness in our xy plane should be the same. So here C11 should be equal to C22. Right? So if we assume this type of material, then we can further reduce number of elastic constants. So here we are writing C11 is equal to C22, and shear stiffness, the stiffness related to the shearing force, the shear stiffness in the xz plane here and yz plane here, we should have the same strength. So epsilon y z must be equal to epsilon zx. Okay, and for that case, C44 and C55 should be the same. And if you consider axial compression or axial tension, in such cases, our strain along x direction and strain along y direction should be the same. Okay, and to achieve that, our C13 and C23 should be the same. If we achieve epsilon x and epsilon y to be the same, then we should have CY3 and C23 as the same. And one more thing we'll observe, the C66 is coming as your C11 minus C12 by 2. Okay, so now for a transversely isotropic material, we have total 9 minus 4 means 5 independent elastic constants. For a transversely isotropic material, we used to have 5 independent elastic constants. Now here, for a transversely isotropic material, we used to have 5 elastic constants, and this 5 elastic constant can be written in terms of our engineering constant like this. Here we have 5 elastic constants here: E, Poisson ratio, Ez, Poisson ratio in the Zx plane, and our shearing strain in the Zx plane. So 5 independent elastic constant can be correlated with respect to our engineering constant like this. Now, if you consider fully isotropic material, in such cases, our elastic constant can be reduced to 2. From 5, we can reduce to 2. And here you can see for a fully isotropic material, we can write our strain stress relationship like this as per our generalized Hooke's law. And we can write in a matrix form like this. And here you can see that we have 2 independent elastic constant to represent isotropic material. Here, this part is corresponding to shear modulus G. Since we know that G is equal to E by 2 into 1 plus mu, you can see that we used to have 2 independent elastic constant for a isotropic material, either E and mu or E or both. Okay. So now here, what we have achieved is that for a ideally or fully anisotropic metal, we used to have 81 elastic constant. For a generally accepted anisotropic metal, we used to have 21 elastic constant. For our monoclinic metal, we used to have 13 independent elastic constant. For a orthotropic metal, we used to have 9 independent elastic constant. For our transversely isotropic metal, we used to have 5 independent elastic constant. And for our isotropic metal, we used to have 2 independent elastic constant. Okay. So here, you also have observed, that independent elastic constant also can be written in terms of our physical quantity E and the nu. For our isotropic metal and orthotropic metal, we can write our elastic constant in terms of our physical quantity like this. Okay. So number of independent elastic constant here will be the same number of independent constant here also. I hope you get some idea. Thank you.